All right, so hopefully everybody had a good week off last week, uh, stayed healthy, and hopefully did a little bit of mechanics and materials during your off time. So first thing, just remind you, we do have a test coming up tomorrow. Is our second test. We'll just go up through section 5.5. That was the last section we did in chapter 5, where we're twisting circular shafts. So what we're going to do today is we're going to talk a little bit more about shear and moment diagram, and then we'll stop and then spend the second half of our class time discussing the test, give you a chance to ask some questions, so on and so forth. So that's the plan for today. And let's see. I don't need that. All right, so this is what we're going to start talking about today. We're not going to finish this, and probably we're not going to have time to go through an example. Just basically kind of verify and prove something that we discussed at the end of class last Thursday. I know it was a long time ago, but what we're going to start talking about today is what I'll call the graphical method for drawing move this out of the way. Shear and moment diagrams. All right, so first off, so a quick reminder, what we call the shear and moment diagrams are literally a graph showing what the shear force and bending moment is down the entire length of the beam. And the reason we need this is we're going to analyze the beam and calculate what the maximum shear stress and what the maximum bending stress is. We need to know what the maximum shear force is and what the maximum bending moment is. And that's the purpose in constructing these diagrams. Now, what we did, that was whatever, last Thursday we met. I don't remember what date that was, June something. We did this by actually calculating what the equation was as a function of x being the longitudinal direction down the beam. We got an equation for the shear force and the moment as a function of x, and literally graphed those equations. What we're going to talk about or start talking about today, again, what I'm calling this graphical method, this is a way to draw the diagrams without having, it's an 8, to derive the equations for, say, v of x and m of x. Again, we've got a beam, x our longitudinal direction. That's how we did it to start with. We used method of sections. We went out there some arbitrary distance x and cut it, and we found what the shear force and bending moment was at that arbitrary position x. Solve for those. Remember, we had to cut it where the load changed, because our equations will change when the load changes. Well, what we're going to hopefully be able to do, or you'll be able to do, I can already do this, but hopefully not after today, but you'll be able to draw those shear and moment diagrams without having to actually calculate those equations. It's a lot quicker, shorter, easier, less work. Now, it is important that you know how to find those equations. That's why we spent that day before our break, going through that is, and you'll see later when we start talking about beam deflections, how much is this beam going to deform? We're going to need the equation. So you're going to have to be able to do it eventually later, but you don't actually have to calculate those equations to draw the diagram. And so I just wanted to look at one specific example or situation today, and then that'll probably be all we'll do with this today. And we'll start talking about the test. But I want to look at what if we have a region of concentrated, okay, spell that right, concentrated force or concentrated moment. So we're just going to look at, in general, if we've got some beam, and we'll just make it simply supported. Put a pin support at one end, a roller support at the other. And if we come out here at some point, I'll just call it A, and we're going to apply a concentrated force at that point. We'll call it FA. And maybe we also have a concentrated moment acting there. This is just an applied moment acting at that point A. So what we're going to do is look at, what happens to the shear force and the bending moment just before point A, where that load is applied, and compare it to what's the shear force and bending moment just after point A, and compare and see what happens to the shear force and bending moment. And then we'll be able to use this in general anytime we have a beam, when we run into a concentrated force or we have a concentrated moment. We'll know how the shear force and bending moment change, and we don't have to actually calculate those equations. So what we're going to do is we're going to come in here and cut this beam just before and just after point A. This is going to have some infinitely small length. We'll call it dx. All right, and so I'm going to come over here and draw a picture, blow this thing up so it's bigger so we can see it. And so, here's point A. All right, our x-axis is running along this way. We'll put our coordinate system over origin at the left end. And at point A, we've got this force denoted FA, and we've got this applied moment called MA. And they're acting right there at that point at A. This thing's got some width or length, whichever way you want to think about it, dx. And so we want to know what is the shear force just before we get to point A. And notation wise, I'm going to call this dA minus. Likewise, we want to know what the moment is right before we get to point A. I'm going to denote that as MA minus. And we want to know what is the shear force and the bending moment just after point A. And we'll denote those as dA plus and MA plus. So we're kind of using some calculus notation you might have seen before in one of your calculus classes. The plus and minus here really has nothing to do with direction. The plus and minus is just used to denote minus, meaning just before you get to point A, and anything with the plus subscript, or be subscript, is denoting values just after point A. Okay, and so that's what we want to see, is what's the difference between the shear force before we reach this point where that concentrated force is applied compared to what it is just after. What's the moment just before and just after? How does it change? Right? That's our goal. So what we're going to do is we're going to sum the forces in the y direction. Right? This is in equilibrium. Right? Everything we deal with in this class is in equilibrium. So I know when I'm looking at this free body diagram, right, all the forces in the y direction have to add up to 0. So I've got VA minus, and I'm taking positive as up. So I assume this was going up, so that'd be a positive. But we got FA, our applied force, going down, so minus FA. And then VA plus over here, I assumed it was going down, so that'd be minus VA plus. Oh, it's got to add up to 0. So let's solve for VA plus. So VA plus is the shear force just after point A, where that applied force is equal to VA minus that applied force. So what this tells me is the shear force just after this applied load is equal to the shear force right before that applied load minus that applied load. So what that tells me is the shear force, if you're talking about the diagram, it's going to go down because it's going to decrease. We're subtracting that applied load. So the shear force is going to decrease by whatever that applied load is. So if I've got a beam like this and I'm trying to draw my shear diagram, whenever I come to an applied load like this, my shear diagram is going to go down whatever that applied load is. Right, now, a couple of things just to keep in mind here. This was for the force acting down. The exact opposite would happen if your applied load was up. So just make note of that. So V would go up, whatever FA is, if FA was directed upward. Right? There's no need for me to go through this exact same thing with the applied load FA going up. The opposite is going to happen. It's going to go up whatever that applied force is. Other thing maybe to note here is notice that applied moment, MA, had no effect at all on the shear force. Right? So just remember, make note of that. MA has no effect on V. So whether you got an applied moment there or not, has no effect at all on the shear diagram. Right? The shear force is only going to go up or down whenever we have applied forces. Right? Right, any question how we got that result? In fact, let's see. Let me find. We kind of talked about this last Thursday, but again, it's been a while, so I think it might be worthwhile to maybe revisit this. This was our shear and moment diagram that we drew and constructed whenever Thursday, last day we met, and just remind you and reinforce exactly what we just proved in general. We know it's going to happen. And so if you look at our beam here, we've got this applied force of 30 kilonewtons. So what did our shear went down 30. Then we come along the beam, and when we get to this pin support, we've got our reaction force By, which was 56. Our shear diagram went up 56. We continue along the beam. It doesn't change until we get to this next applied force, 50. And our diagram goes down 50. And then finally, when we get to the end, we got our support reaction dy, which was 24. And this is a way we can kind of check ourselves. If we don't wind up where the same value as our support reaction force there, then we know we did something wrong. So now that we know what we know, basically all you got to do is calculate the support reactions, and you should be able to draw the shear diagram without doing any other calculations, really, unless, subtracting numbers. If you're at minus 30 and you go up 56, you got to do a little math. But we don't need those equations that we found to draw that shear diagram. All right? Any questions about what a concentrated force does to our shear diagram? All right, well then let's go back to where we were. Now that example I just had up there from last time, we didn't have a concentrated moment on that beam, so we can't really look and see. Go back to that one and look and see, but let's we'll do an example Wednesday when we will have a concentrated moment. But let's sum the moments about point A and see what we get. And I'm going to take positive counterclockwise. So we're summing the moments about this point A, where our force FA is applied. So that's not going to cause a moment. We do have our applied moment, MA. So we'll start with that maybe. Then we've got our two moments, MA minus and MA plus. I assumed MA minus was going clockwise, so that would be a minus, MA minus. I assumed MA plus was going counterclockwise, so that's a positive, MA plus. So I got the three moments that are acting on this. Now, notice these two shear forces, VA minus and VA plus, they do not go through point A. Right there, if this is dx, this would be dx over 2. This would be dx over 2. That's where those two act. So they're going to cause a moment. The VA minus is causing a clockwise moment, so it'd be minus VA minus times that distance dx over 2. And VA plus also causing a clockwise moment. I got a question. What we're doing in chapter 6 is not on your test. Tests, you're just responsible up through chapter 5. This will be on test 3. So our shear force VA plus causing a clockwise moment, so minus VA plus times that distance dx over 2. All right, now let's got to add up to 0. All right, well here's where we can do something nice, and that is dx is infinitely small. So dx over 2 is even smaller than that. So you take something infinitely small and divide it by 2. So essentially we're going to say dx over 2 is essentially 0. Right? So the moment that's caused by these two shear forces, it's so close to point A that it's really not going to cause a moment. And so that all we have left to consider and deal with is our moments. And just like we did up there, we want to solve for the moment just past point A. So MA plus, and solve for that, it's going to be equal to, move this to the other side, becomes positive, MA minus, and then minus MA. Right, so what this says is the moment just after where that concentrated moment is applied is equal to the moment just before it minus that applied moment. So just like up there, it tells you the moment decreases or is going to go down by whatever that applied moment is. Now, just like up here, this was with the force. I assumed MA was clockwise, so that's going to be true for a counterclockwise moment. So if you've got a counterclockwise applied moment like this, when you're drawing your moment diagram, just like the shear diagram went down whatever that applied force is, the moment diagram is going to go straight down whatever that applied moment is. And the opposite would happen if the moment was in the opposite direction. So the moment would increase by MA if MA, your applied moment, was clockwise. That one you got to, maybe it takes a little more effort to remember the right direction. It's kind of intuitive with the force. The force acts down, you go down. The moment doesn't go up or down, it goes counterclockwise or clockwise. So it's not necessarily intuitive. This is something you're just going to have to remember, that if you got a counterclockwise moment, right, you're going down. If you've got a clockwise moment, your moment diagram goes up. And again, that example we looked at last time didn't have one of these, so we can't go back and look at that. But we will see some, starting, I reckon, Wednesday, where we will encounter a concentrated moment. But now we know what to do when we're drawing our moment diagram. If we run into one of those, we just go up or down whatever MA is. Right? And it's going to really help us be able to draw these diagrams without calculating those equations. All right. So any questions at this point? What to do for shear moment diagrams if we have a concentrated force or concentrated moment? All right, so that's a good place. We'll stop there as far as the shear moment diagrams go today. We'll pick this up on Wednesday. We'll talk about what if we have a distributed load acting on a beam, because that's the other type of loading that we frequently encounter, and we need to know what that does to the shear and moment diagram. That's what we'll do first thing Wednesday. So unless somebody speaks up, I'm going to move my sheet of paper, and then we'll start talking about the test. All right, take that as we're good for that today. All right, so where did I put my pen over here? All right, so again, this is test number 2. And repeat, this just goes up through 5.5. Right, nothing we've talked about in chapter 6. You're responsible for the test tomorrow. All that'll be on test 3. Basically, like the first test, this is going to be closed book notes. There is no formula sheet provided, but we'll look at this in a minute. And there's not that many formulas that you got to worry about. So keep this in mind as you're preparing, studying. Closed book notes, it's all you. Now, sort of related to the, as far as no formulas provided, now any material properties that you'll need that you would get out of that table that's in the back of your textbook, that would be provided. So don't think you've got to know what the coefficient of thermal expansion is for A36 steel. That you don't need to know. The material properties, any E modulus of elasticity, or shear modulus, coefficient thermal expansion, any of those material properties, those will be provided. So material properties provided. There are 4 problems on the test, in case you're wondering or curious. As always, remind you units. Most people did pretty good on the first test about putting units and making sure they're correct units. But I always like to remind you that. And a couple other suggestions, reminders. Make sure you show all your work. Again, if you skip a lot of stuff, I can't tell sometimes, where you went wrong. So you want the maximum partial credit. If you make a little mistake, if you show me all your work, I can see you just made a little mistake. Yeah, we're going to get to that. Somebody asked a question. We're going to go over the formulas in just a minute. Sort of related to this, I know, like on that first test, there was that one problem where you really didn't have to do any calculations. It just asked you, basically look at this graph and give me an answer. Make sure you put all your answers on the sheet that you're going to email me. So anything you want graded, it has to be on that sheet that you send me. I am not going in and looking at the answers that you submitted in Canvas. That's really does nothing other than, if you're curious and you want to know if you got the right numerical answer, you can submit it. Wait till you work all the problems before you submit it in Canvas. But if you're curious and want to know, if you got them all correct, you can submit it and it'll tell you. But I don't look at that. I'm looking at your work that you email me. Okay, so make sure you email me everything you want me to grade. And probably sometime this afternoon, I'll resend out that email that they listed the procedures and steps to follow. But basically, it's the same as the first test. You'll log into Canvas, open your quiz. You'll have to go through the honor lock verification, and then once it opens, you'll have 60 minutes to work the 4 problems. And make sure once you scan it and email it to me, shortly I should respond to you with an email telling you I got it. If a little, 15, 20 minutes passes and you hadn't gotten an email back, you might want to send me an email and make sure that I did get yours, okay? All right, so any kind of procedural or general type questions before we start looking at specific, mechanics and material stuff? All right. So basically, again, our test here is covering chapters 4 and 5. And one formula everybody should know, like some of these problems, it asks you to calculate the normal stress. So everybody should know normal stress P over A. And if you don't know that by now, you haven't been working any problem. And that's the other thing I can, sort of general thing is, study homework. The problems on the test, they're going to be similar. These 4 problems, they're going to be similar to the homework. So that's the best way to prepare, is just to work. And some of these problems in chapter 4, they ask you to calculate the normal stress. It's P over A, so everybody should know that. But for the most part, in that first section, 4.2, we were getting axial deformation due to an axial load using this formula, PL over AE. P here is the normal, the axial force. L is the length. A is the cross-sectional area, and E is the modulus of elasticity. That's one of those material properties that would be provided. So maybe we'll just kind of take this section at a time. Any questions related to this section and applying using this formula? I will remind you, in that section, there were some of those problems where you had, the load changed, or the material changed, or the size cross-section changed. And so you had to break it up into pieces and get the deformation of each section. And you would have to add all those up to get the total change if you were asked for that. Any questions from that first section, chapter 4? Taking silence is a no. Well, the next section, there really wasn't any new formulas to deal with. And the next thing we did was the statically indeterminate. And basically, it just used a combination of equilibrium and deformation. So equilibrium, again, if you're in this class, you should know the 2D equilibrium equations. Some of the forces in the x and y direction, 0. Some of the moments are at point 0. The deformation, that's that formula. Okay, I have a question. Let's see. Hang on a second, I gotta get my book. Somebody asked about number 20. I gotta get my textbook here. All right, so I'm looking at the picture now. We got 3 titanium rods and a rigid bar AC. All right, so I can stick this up here real quick. Everybody can see. This problem down here. So I got another question. It says, can you also do conversations? I'm not sure what the question's asking. Christopher, if you could, I don't know. What conversions? I'm not sure what conversions you're talking about. At this point, we haven't got to anything. We'll get to that. We'll talk about that when we get to chapter 5. All right. So, question. This one is, when you add the total deflection, why do you not add deflection AB in there? Well, let me draw this picture. Let's look at that. So what we've got, and again, this is in section 4.2. And now I messed up. All right, so we got this thing is rigid. So we got a bar attached here. This is this pin here. This is AB. And over here, we got another one pin at C. And that's B. All right, and we got this one pin here. This is E. And this is F. All right, so this one is rigid. So that doesn't bend. All right, so when we apply this force, this 60 kip force here, right? It wants to know this problem, 420. basically asks, how far does point F move? Right? This point F, how far is it going to move? All right, well, it's going to move due to three things. One, obviously, EF is going to stretch, right? We're pulling on this thing, it's in tension. So EF is going to stretch. But AB and CD are also going to stretch. Now, I don't know, yeah, they're the same length, but they're different sizes. So the area for AB is 1 square inch. The area for CD is 1.5. So they're not going to stretch the same amount. They're the same material. I'm looking at this over here. They're the same length, they're the same material, but the cross sections are different. So CD is bigger than AB. So it is not going to stretch as much as AB. So if I draw sort of a, we'll put my points here, A, C, D, and D. All right, so AB is going to stretch some. Okay, so AB is going to stretch out here some distance. We'll call it delta AB, which is going to be PL over AE for that one. That's how far AB is going to stretch. CD is not going to stretch as far. It's bigger, right? But it is going to stretch. So maybe we'll call this A prime and C prime, right? But this is now going to be at an angle because this delta CD is PL over AE for that one. It's bigger, so it's not going to stretch as far. And then we're going to have, F starts here. It's going to wind up out here, some point F prime, and we're going to have this deflection, delta. This is E. So delta EF is going to be PL over AE, however much EF stretches. So you're just going to have to do some geometry because you're trying to get, this thing starts. Yeah, maybe my picture didn't turn out too good. So we'll call this will be E prime. So that distance, you're going to have to get just from some geometry. All right, if you're looking at, if I can draw this maybe better. So E starts here and it's going to go to E prime. A prime. C prime. So that distance, again, this comes from here. And then this distance here is that one. There's a bunch of different ways you can get there, but it's just geometry. That's how far he's going to move over. And so delta F, the total, would be whatever delta EF is plus, I'll call this delta E. So you'd add those together to get the total distance that F's going to move. All right? That make sense? Get my pen out of there. All right, let's back up then. Statically indeterminate. Again, there's no new formulas. You're just using a combination of equilibrium and what you know about deformation. All right. Well, the last section, the last thing we did in chapter 4 was the what we call thermal stresses. Which, again, stress is due to if it's constrained or not. So, and in 4.6, this is where we did the thermal stress was alpha delta T times L. So that was one of the new formulas you're responsible for. Alpha is that coefficient of thermal expansion. Material property, that would be given. Delta T is change in temperature. L is the length before that temperature is applied. And to get the total, right, is you got to add the force due to the deformation due to any axial force, delta P from before, and the change due to temperature. Those added together give you the total deformation. Questions related to temperature change?
When your beam is fixed, does that equation equal 0? The S total or delta total?
When you say that, you're talking about something like this where it's fixed at each end.
Right.
Yeah, it can't deform. It can't get longer. It can't get shorter. Right? If it's constrained, fixed at each end, it can't get longer or shorter. Now, if the temperature goes up, it wants to, but those fixed supports push it back in and prevent it from moving. So for a problem like that, the total would be 0. Right? If you add up those two, it would be 0. So here, the total, you add up delta P plus delta T, yeah, that's the delta, would be 0. Yeah, if you have one, where, say it didn't go all the way to the wall, we looked at one, worked an example like this, where, I don't know, this is some little distance, just call it X. Well, if the temperature goes up enough to where this does expand to where it hits that wall, here the total, when you add those two together, would be whatever that distance X is. Right? Because it can't go any further than that. It hits the wall.
Gotcha. Thank you.
Mm-hmm. Any other temperature questions? So really, again, in chapter 4, as far as new formulas go, PL over AE and alpha delta TL. Those are the two really new formulas that you're going to be applying and using in chapter 4. All right. And so then we got to the twisting, right? We got to chapter 5. Now here we do have a couple of new formulas that you do need to know. Again, the maximum shear stress, TC over J. We're talking about a circular cross section where the outer radius is C. That's what the C in this formula is. J is the polar moment of inertia. And for a solid circular cross section like that, J is pi over 2 C to the 4th. Again, C is that outer radius. Now, if you do encounter a hollow cross section, a hollow tube that has a cross section like this, you're going to have an outer radius and an inner radius. Here, J would be pi over 2, the outer radius to the 4th minus the inner radius to the 4th. Really, if you know this formula, you should get this, because all you're doing is taking the moment of inertia for the big circle and subtracting the moment of inertia for the whole, the little circle. Somebody mentioned conversions. Everybody should I'm gonna hold you responsible for this one. It'll be the only conversion that I would, as far as something that you might have to memorize, is that 1 horsepower is 550 foot-pounds per second. So that one, not saying you'll need it, but if you do need it on the test, that's one you need to know. I'm not gonna provide that for you. One other formula as far as these twisting shafts go, if you're looking at a drive shaft and you've got power involved, right? This one is another relationship you should know, that power is equal to the torque times the angular velocity. This is omega. And for this formula, omega here must be in radians per second. So it's very common, if you worked any of these problems, a lot of times they'll tell you it's rotating at so many RPMs. Well, to use this formula, you can't put RPMs in there. You need to convert that to radians per second. But that involves something everybody should know, right? If you've got revolutions per minute, right? 1 revolution is 2 pi radians. And then to get rid of the minutes, 1 minute is 60 seconds. And so if you're given RPMs, you multiply by 2 pi, divide by 60, that'll get you radians per second, right? The revolutions cancel, minutes cancel, and we're radians per second. But that's something you should know. It's not a really new formula to. I would hope everybody knows that 1 revolution is 2 pi radians, and there's 60 seconds in a minute. But so this formula, again, you need to know the relationship between power and torque. That's the T is torque. That's the twisting moment. P is the power. All right. Any questions related for his twisting shafts, shear stress, polar moment of inertia, torque and power? All right, well, the only other formula in chapter 5 was when we talked about angle of twist. And so the angle of twist, phi, TL over JG. That is a formula that you do need to know. Again, this is, if you're looking at this circular shaft, you apply a torque to this thing. That angle that the cross section rotates through, that's what we call the angle of twist. And the only new thing in this formula, G, that is the modulus of rigidity. That's shear modulus of material property that you would be provided. T is the torque, L is the length, J we discussed already. It's the polar moment of inertia. And let me go ahead and write this down, and we'll just open up to any questions. That last section we did, again, was the statically indeterminate. And again, just like before, it's really not anything new. It requires, equilibrium. Here, some of the torques equal 0. And deformation, or what he calls it compatibility, condition that if you've got something like this, see, right there where these two sections meet, the angle of twist has got to be the same. So the angle of twist of C with respect to A has got to equal the angle of twist of C with respect to B. The only way that's not true, if it's not true, means one twists more than the other, it means it broke. So as long as it doesn't break, then that angle there has got to be the same. And again, the angle is TL over JG, and then some of the torques equal 0. You got to use a combination of what we know about equilibrium and deformation. that's it. That's what your test entails. That's what as far as formulas go. That's what you need to know. Best way to prepare is if you haven't been working a lot of problems, then I suggest you get busy this afternoon, this evening, and start working. That's what you're going to see tomorrow. You're going to have 4 problems to solve. It's not going to be, any prove this, derive this, fill in a blank question. It's going to be solve this problem. All right. Questions about anything? Well, as always, I'll stop recording here in just a second. But I'm more than happy to hang around. You got, additional questions that whatever reason didn't want to ask right now. If you want to ask them here in a few minutes, I'll stick around and answer any questions that you have. Otherwise, if you don't stick around and have any questions, that's it for today. Don't forget about the test tomorrow. Make sure you log in. Just like before, I'll go in and publish it, open it up for you a little bit before 11. So if you want to get started, a little before 11 tomorrow, that'll be fine. Just keep a check on it, and somewhere between 10:30 and 11, I'll go in and open it up. And but again, you get 60 minutes once you open it up and actually start working, regardless of when you start. All right, so I'm going to record. And again, got questions? Stick around. If not, good luck tomorrow.